great pleasure to welcome Professor Dr. David Vogan from MIT to speak. He's been kind enough to take time out of his busy schedule to come here. So I thank everybody for coming. So let me introduce the speaker. Dr. David Vogan is Professor of Mathematics and President of the American Mathematical Society. He received his BA and MS degree from the University of Chicago in 1974 and the PhD degree from MIT in 1976 under the direction of Bertrand Costa. Professor Vogan served as an instructor and member of the Institute for Advanced Study before joining the MIT Mathematics faculty in 1979. His research interests include group representations and Lie algebra. Professor Vogan is a member of the research group Atlas of Lie Group in Representation, which in 2007 computed the character table of the Lie Group E8, attracting a great deal of international press. Professor Vogan served as the chair of the undergraduate committee from 1984-1985, 86-87, 96-97, and of the graduate committee in 1993-94, 95-96. Professor Vogan chaired the Pew Mathematics Committee in 1997 to 1999, before serving as department chair and head in 1999 to 2004. The former Sloan Fellow, Professor Vogan was selected by the department faculty as the Robert Collins Distinguished Scholar in 2007. In 2011, Professor Vogan received the AMS Levy L. Conant Prize for his article, his character table for E8. He's currently a fellow of the American Academy of Art and Sciences since 1996, and a member of the National Academy of Sciences 2013. So it's a great pleasure that I welcome Professor Dr. David Vogan to the seminar.
So thank you very much for the, I'm supposed to stand close to the microphone. Thank you very much for the invitation. So I'm going to try mostly to be comprehensible, and I know that I won't succeed all the time, so you should feel free to look puzzled, and I'll try to slow down or say more words or something like that. So this is more or less what I, oops, let's see if I can get rid of the little hand. Okay. Actually, I think I am going to stand where I can see the, what I'm going to talk about has its origins in linear algebra, in solving systems of equations by Gaussian elimination. So what you do in Gaussian elimination is you make a bunch of equations with a bunch of unknowns simpler. Roughly speaking, you want to reduce the number of unknowns by one. That's the key step. And what I'm going to do is talk about how that is related to geometry, to studying arrangements of lines and planes and things like that. And what happens in geometry that corresponds to reducing the number of unknowns by one is relating some geometry problem to a geometry problem in a smaller dimension, to make life simpler by making it lower dimensional. So here's a picture. There's a simple geometric object. Actually, what I'm going to do here is make it more complicated by adding a dimension. So every place I had a point on my stick figure, I'm going to make a circle. And I end up with going from this stick figure on the left to the actual Michelin man on the right. And that's the whole idea. It is relating simpler geometry to more complicated geometry. So how's this going to go? So here's a system of 3 equations and 3 unknowns. And I'm always going to look at systems that have only one solution. So how do you go about solving this? Well, the easiest case to solve, this is a special case, when the system just looks like this. And the way you solve it is you divide each of those equations by the coefficient of the unknown, and there's the solution. So that's not rocket science. So the slightly more complicated case is this lower triangular system. And the way you solve this by Gaussian elimination is you add some multiple of the first equation. I've got a pointer here somewhere. Let's see if I can. Well, oops. So maybe I don't have a pointer. Let's see. I had a really nice old one of these things, and there was some thing that I was at where somebody didn't have one of these things, and so I loaned him mine, and I got it back at the end, but without the little USB thing that plugs into your computer, so it was completely useless, so I had to get a new one, and I haven't figured out how the new one works. Oh, there's the pointer. Whew. Okay, so the way you solve this system is you add some multiple of this first equation to the second one to get rid of that x1, and you keep going like that. Always you add some multiple of one of the equations to a later one, and in the end it turns out to be diagonal. So here's a slightly more complicated equation. It's not lower triangular now. But you can do the same kind of thing. You can add a multiple of the first equation to the second one, and what you can get is you get rid of this variable here. See, so I added some multiple of that to get rid of that, and that's what came out. So this equation now is again lower triangular, except that the variables are in the wrong order. Basically, it's lower triangular. Okay, so that's the easy part of Gaussian elimination. So here's the kind that really shows up on the linear algebra test. You get everything's non-zero. So in this typical case, this coefficient here isn't 0. So you add multiples of that first equation to the other ones, and get rid of those coefficients in that column. You're left with this. Again, typically what happens is that this coefficient here isn't 0. So you can add a multiple of it to this equation to get rid of that thing, and you're left with that. And again, this system is sort of like lower triangular, except that the variables are in the wrong order. But this is one of the ones that's easy to solve. So that's everything about Gaussian elimination in 3 variables. So I want to say a little bit how this looks in general. I want to write use some matrix notation. Don't worry if this isn't happy for you. So instead of writing a system like this, writing out all the numbers, I'm going to this is shorthand for the same thing. I've got some bunch of coefficients and a bunch of unknowns, and this is the equation I want to solve. So here's what happens. That if you've got any system of equations like that, then you can do 2 things. You can divide one of the equations by a non-zero constant, or you can add a multiple of one of the equations to one lower down. So in linear algebra, people don't usually emphasize this just lower down business, but mathematically it's a nice thing to do. I mean, if you really just want to solve the equations, you might as well add something to an earlier equation too. That'd be just as good, but mathematically it's nice to restrict things. So anyway, if you keep doing stuff like this, you can end up with a system that is essentially lower triangular, except that the variables are in some funny order. So that's the story. So how does this look? So here's what happens with these 3x3 matrices. If you start with a lower triangular system, so all these coefficients up here are 0, and do that business of adding a multiple of an equation to a later equation, you end up with just this coefficient matrix. Everything's 1. There's just one thing like that, easy to solve. The next most complicated things, well, if now you've got something non-zero in this one place above the diagonal, then by doing this subtracting, well, adding multiples to later rows, you end up with a system that looks like that, and easy to solve. The other possibility is that if you had just one entry above the diagonal there, then you end up with something that looks like that, or these slightly more complicated things. And finally, the sort of generic situation that I wrote last, where after you do all the rearranging stuff, you end up with a system of equations looks like that. Okay, so I said that all these systems you end up with are lower triangular, except that you have to rearrange the coordinates to see that. So I've written here a permutation. I've rearranged the numbers 1, 2, 3. That tells you how you have to rearrange the coordinates to make it lower triangular. So up here, if I want to make this lower triangular, I have to reverse the coordinates. And there's something similar written in the other 6 cases. So there are sort of 6 possibilities here. And this one on top is the sort of generic one, the one that usually happens, but the others are possible too. Yes?
So can you have, you did the first row and the second row, can you have the third row, or is that some linear combination of the other two or something? When you went to the first two.
Okay, so how do I say it? I've written down here some conditions on the coefficient matrix. So in the first case, the condition is that all 3 of these entries above the diagonal are 0. Then here I said, well, if you allow just one of these entries above the diagonal to be 0, this is what happens. Or if you allow just this to be non-zero, this is what happens. So you are sort of asking, well, what if you just allow this entry in the upper right corner to be non-zero? Well, that ends up getting counted in one of these places. So it's there, but I just choose to organize them like this. Okay, so what's this have to do with anything? So I want to talk about those same ideas in terms of geometry. So one of the most basic ideas for mathematicians about geometry is the idea of a flag. So in a three-dimensional space, what a flag is 2 things. It's a straight line through the origin and a plane that has that line in it. So if you want to pick a flag, you first of all have to pick a plane through the origin, and then in that plane you have to pick a line. So there's a picture of a flag. So first I picked this maple nose beautiful colors, but I don't know their names. Anyway, this plane, and then you pick a line in that plane. That's a flag. Well, one flag's not so interesting. What I want to talk about is all the different possible flags in the world and what they have to do with each other. So if you have a system of equations, well, in three variables, you've got a 3 by 3 matrix. And out of a 3 by 3 matrix, you can make a flag. The way you get the line is you look at all the multiples of the first row of the matrix. The first row of the matrix is some vector in 3 dimensions. So all the multiples of that, that's a line. If you look at the first 2 rows of the matrix, that gives you a plane. The first 2 rows span a plane. And so out of any system of equations in this way, you get a flag. Well, different matrices can give you the same flag, but the reason that I put these operations earlier is that they're how you tell when 2 matrices give you the same flag. For example, the line is all the multiples of the first row. So if I multiply the first row by a constant, I don't change that line. And in fact, well, these operations don't change the flag, and that's the whole story. So the conclusion is that there are 6 kinds of flags. There are 6 kinds of flags in 3 dimensions. Well, I mean, you could say a lot of things about what kinds of flags there are, but I want to talk about 6 kinds. So the way I want to talk about kinds of flags is there's one special flag. If you work in 3 dimensions, then you've got the x-axis. There's sort of a preferred line, the x-axis. That's our first line. And then you've got the xy plane. That's a preferred plane. So this flag all by itself is special. That's the x-axis sitting in the xy plane. That's just one flag. So I'm going to list all the other flags in terms of what they have to do with this special flag. So here I'm going to list all the flags where the plane is the xy plane, but the line is some line in it that isn't the x-axis. Over here, I'm going to list all the flags where the line is the x-axis, but the plane is something that has the x-axis in it, but isn't the xy plane. And so on. Up at the very top is a sort of generic flag. So the most general thing that can happen is that my line is not in the xy plane, and my plane doesn't have the x-axis in it. That's the sort of general case. So 6 kinds of thing. Okay. So in this picture, as you go up in this picture, the geometry gets more complicated. Down here, I've just got one point, one flag, and up at the top, I've got more or less all the flags in the world. So as you go up in this picture, the geometry gets more complicated. And what happens is that if you go up one step, always what was happening was that one particular line got replaced by any line in some plane. And if you went up, well, I had some of the steps colored red, and in that case, I had some line, and I was starting with a particular plane that had that line in it, and I replaced that by any plane that had that line in it. So if you have a plane in mind, all the lines in a plane, well, have I got a picture? Yeah. So basically this is replacing points by circles. So here's a picture. Here's my basic flag. Now this is terribly drawn because this line is supposed to be the x-axis, and this plane is supposed to be the xy plane. And now when I go up this blue step, I want to look at my plane is the xy plane, but the line can be any line in the xy plane. So, this is a picture of all the flags that are possible over here. Instead of, well, I've got the xy plane, and instead of just this x-axis in it, I've got any one of these lines in it. So I've replaced that single line by a whole circle of lines. I've replaced a point by a circle. Same thing over on the other side. Instead of looking at, I'm still fixing the x-axis, but instead of putting it in the xy plane, I look at all the possible planes that have the x-axis in them. And that's this circle of planes here, all the planes that contain that one line. So that's what moving up in the diagram is, making points into circles. So what's a Schubert variety? Well, so here are the Schubert varieties in 3 dimensions. The smallest Schubert variety is this x-axis in the xy plane. It's 1 point. The most general Schubert variety, well, let's see if the most general Schubert variety is just all lines in any line in any plane. That's the story. So this medium-sized Schubert variety over here means it's any line that's in the xy plane. Over here, I start with any line which is in the xy plane, and I put it inside any plane that contains it. So this is a bunch of possible configurations of lines and planes. And always what's happening is that when you go up one of these arrows, every point in this small thing is getting replaced by a circle in the big thing, nearly. So I think I don't want to talk about the failing part. Basically, when you go up in this picture, here this x-axis is getting replaced by any line in the plane. So the x-axis, that's just 1 point, gets replaced by any line in the xy plane, which is a circle. So always when I move up, I'm changing points into circles. So I'm not going to... I'm going to try to say this once more. So I'm trying to understand all possible line inside a plane in 3 dimensions. And maybe the most basic idea here, it's another very mathematical idea, is to think about all geometric configurations as a geometric thing. So I'm making a space which is all the ways to put a line inside a plane. And what I want to claim is that the 3-dimensional space. So how many planes are there in 3 dimensions? Well, if you want to give a plane in 3 dimensions, you've got to specify a unit normal or something like that. So you've got to pick a point on the 2-sphere, and then the plane that's perpendicular to that is a plane. So you've got a 2-dimensional space of planes, and each plane has a 1-dimensional space of lines in it. So altogether you get a 3-dimensional space of flags. And Schubert varieties are just pieces of that 3-dimensional space where you say something about how the line and the plane are related to the x-axis and the xy plane. So again, the smallest Schubert variety is the line's the x-axis, the plane's the xy plane. The slightly bigger one is line inside a plane where that prime is supposed to be there. The plane is supposed to be the xy plane, but the line can be anything. And in other words, this is all the lines in the xy plane. It's a circle. It's one-dimensional. And, you get from this single point to this more complicated thing by inflating this point into a circle. So I'm going to skip this tricky part one. So here's what you need to do computations with Schubert varieties. All that matters is these arrangements of red and blue arrows that tell you how you inflate these little things into the big things. So this picture that sort of came from Gaussian elimination has all the information about how to study Schubert varieties in 3 dimensions. So how do you, where does this diagram come from? Well, there's one entry in the diagram for every permutation, and whenever you interchange 1 and 2, you make a blue arrow pointing up. So if I go from here, I've got 3, 1, 2, and I go up by exchanging the 1 and the 2, that's a blue arrow. And if I exchange the 2 and the 3, then that makes a red arrow going up. The 2 and the 3 start out in the right order on the bottom and get into the wrong order when you go up. Okay, so that's the 3-dimensional version. Here's this picture here is the 4-dimensional version. You can do as many dimensions as you want. There's one entry for every permutation, and whenever you exchange I and I plus 1, you put an arrow going up, and you need n minus 1 different colors. So if you start counting things in this picture, that's telling you about the geometry of Schubert varieties. So I wrote some things which I'm going to skip. And well, so that picture that I was just describing, where there's sort of a graph-looking thing with one vertex for every permutation, that has something to do with invertible n by n matrices. That's where the connection with solving systems of equations came from. And invertible n by n matrices, mathematicians call that a real reductive Lie group. And they look at other real reductive Lie groups, and every real reductive Lie group has a picture like that. So here's a picture like that. This one is for a, well, it says it's a, there's a close-up. This is for a 45-dimensional group called SO55. And there are 251 of these little vertices. Since this code that did this was written in C++, they're numbered from 0 to 250, but 251. And every arrow is telling you about the geometry. Every arrow means make all the points into circles. Okay, so what do you do? So, well, the graph that I started with, it has information about Gaussian elimination. It's actually interesting information if you want to write computer software for solving systems of linear equations using Gaussian elimination. You want to know what kinds of configurations can come up and how often and things like that. And all that information is hiding in this graph. So there are a lot of math and physics problems that get related to these other things called real reductive groups. And it turns out that you can do a lot of computations on this graph. So well, if you want to do problems about representation theory, yes?
Would this procedure help you to find the most preferable path to take to minimize round-off error?
That's a great question, and I don't know the answer. Probably there's information there, because at the very top of this graph was sort of the generic case, the case when sort of everything in sight was non-zero. And if you take round-off error into account, that's where you always land. I mean, this is a very standard problem in computation, is that there are some very special cases that may behave badly, but in practice you hope never to see them. And so if you're doing Gaussian elimination, you might want to hope that this coefficient in the upper right corner is never zero, and you just divide by that to get rid of the last column or something like that. And if you write your code to do that, usually it's fine, but it can be fed something which makes that code crash by putting a zero there. So these problems about what are the common cases are somehow related to round-off error problems, but I don't know anything good to say about that. So in 1979, Kazhdan and Lustig showed how to do a bunch of computations in these graphs. They defined things called Kazhdan-Lustig polynomials. So you start with any two vertices in the graph, and they defined a polynomial which has to do with how complicated the graph is when you try to connect x and y. And in particular, they told you how to calculate these polynomials, and there's some algorithm for doing that. And what I want to do is tell you a tiny bit about how that computation works. So we've got this graph, and you want to figure out some polynomial attached to any pair of vertices in the graph. Excuse me. And you do this calculation by induction. You start with y on the bottom of the graph, and you work your way up. And for each y, you start with x equals y, and you work your way down. And what you try to do is find a line in the graph going up from x and a line that goes down from y that are the same color. And if you manage to find that wonderful configuration, then this polynomial attached to x and y is the same as the polynomial attached to x prime and should have been a y prime here, these two guys. And you know that by induction. If you can't find any lines like that, then you say that this pair is primitive. And then you have to do some slightly harder calculation, which I won't talk about. But anyway, one slightly serious calculation for every one of these primitive pairs. So how do you put this on a computer? So in June of 2002, my friend for decades, Jeff Adams, asked my friend since 2002, Foucault Duclos, to write a computer program. And in November 2005, Foucault finished. So there they are programming. And so Jeff said, well, let's take this 248-dimensional exceptional Lie group, E8, and figure out what all these Kazhdan-Lustig polynomials are, because they're there. And so what do you need? So the first thing you have to do is write down this graph. And for this E8 group, the graph has 453,060 vertices. That's a big number to draw pictures on paper, but it's not a very big number for a computer. And at each, coming out from each node of the graph, there are basically 8 edges. So again, that's not a gigantic thing in a computer point of view. And writing this down in the computer, when Foucault originally did it, this took 250 megabytes of RAM, and the computer took about 10 minutes to do the calculation. Other people have jazzed up the algorithm since then, and it now takes about 30 seconds, but that's fine. Then I said that there were some, well, now you're interested in pairs of elements of the graph. This is where it gets hard. If there are 450,000 vertices, well, that's, I don't know, 4 times 10 to the 5th, I guess. And so the number of pairs of vertices is something like 2 times 10 to the 11th. So there are a lot of pairs of vertices. And too many to write them down in a computer, but we only care about the ones where we can't find this nice edge up and edge down business, these primitive pairs. And it turns out that there are only about 6 billion primitive pairs, tiny. And you could write these down. You might wonder how you write down 6 billion primitive pairs in only 450 million bytes. You can figure that out if you know anything about computers, but that's entertaining to think about. Anyway, it's very fast. So far, we're not even straining a laptop. And then we have to calculate a Kazhdan-Lusztig polynomial for each one of those 6 billion pairs. So what's the calculation? Well, you have to fetch a few kilobytes of stuff you already calculated from memory and do a few thousand integer operations. And so you have to do this once for each of these 6 billion pairs. So the next thing you have to do is, well, you have to keep a record of all these polynomials that you find, and you have to write down the new ones. So every time you write down a polynomial, well, the coefficients, turns out the size of the coefficients, they need 4 bytes to store. And there's something like 20, these polynomials, average degree is like 20 or so. But we didn't know how many of these 6 billion pairs gave you different polynomials. Lots and lots and lots of the pairs give the polynomial 1. So no problem. You write down 1 once, and every other time a 1 comes up, nothing else to write down. So the question is, how many of these 6 billion pairs are distinct? If they were all distinct, well, if this was 6 billion different polynomials and 80 bytes of storage per polynomial, that's 500 gigabytes of memory that you need. And because of the way the computation works, it has to be RAM. Everybody has 500 gigabytes of hard drive, but there's this business of reading from the memory, and if you try to do it with the memory on the hard drive, this step is impossibly slow, years kind of thing, because hard drives are a lot slower than RAM. So, well, and you have to keep track. You number these polynomials as you find them, and you write the number of the polynomial for each one of these primitive pairs, and so that's going to take about 25 gigs of RAM. So the thing we didn't know about this computation was how many of these polynomials were distinct. So based on what happened with easy groups, we hoped that, well, as I say, for easy groups, most of the polynomials are 1, and there's a huge amount of repetition. If you do this calculation for 4 by 4 invertible matrices, the polynomials you get are 1 and 1 plus x, 2 of them. So there are hundreds of primitive pairs, but only 2 polynomials. So we hoped that there might be like 400 million of these polynomials, and that would mean this whole thing would take 75 gigabytes of RAM, but we were kind of worried that there might be as many as 1 billion or so distinct polynomials, in which case we'd need 150 gigs of RAM. And this was in 2006, and 150 gigs was a lot of RAM. So one of the people in the group is named Bern Binegar, really, and he did some experiments which, running partway through the computation, told you how many different polynomials there were going to be, and it became clear that we were really going to need 150 gigabytes. And in those days, as I say, there weren't computers around that pure mathematicians could get, which had 150 gigabytes of RAM. So we started asking people, well, what could you do in pure mathematics with 150 gigs of RAM? And in particular, we asked this guy, Noam Elkies at Harvard, and he told us you don't need 150 gigabytes. Because instead of doing these computations that we were doing with integers, he said you should do them in modular arithmetic. We were computing everything with integers. Instead, he said, compute mod 255 or something, and 254 and 253, and when you do all these computations, and then use the Chinese remainder theorem to put things back together, then everything will be hunky-dory. And if you're just doing moduli, if you're doing computations modulo numbers smaller than 256, you only need 1 byte for each coefficient instead of 4. So basically, you cut your memory use by 4. So this is what Noam said, and I started an email to Noam explaining to this poor, stupid Harvard guy why these sophisticated computations couldn't be done with modular arithmetic. And fortunately, I threw away the email before I sent it, but because they can. So this was November 30th that Noam told us that. It took this programmer, Mark van Leuven, 3 days to take the code that Foucault had written and make it use modular arithmetic instead of arithmetic, something like that. That's what C++ is for. You just redefine plus, things like that, no problem. And so finally we were ready to do, we did have a computer that had maybe 64 gigs of RAM. We had access to it. And so we started this computation using all the coefficients modulo 251. And it took 17 hours. So here's the output that came out at the very end. It said that's the elapsed time. 62,575 seconds is 17 hours. I can't possibly do those computations in my head, but I had a calculator. And it finished. And it said that there were 1,181,642,979 distinct polynomials. So that's nice. And it was using basically 64 gigs of RAM. and then the program started writing all these answers to disk. And the writing to disk took 2 days, which didn't seem right, and when we looked into the matter, it turned out there was a bug in the output routine. So that was no good. So fixed the output routine on December 21st. Started doing this computation with modular arithmetic, mod 256. Might as well use the biggest modulus you can. You might, well, anyway, you can do 256 with a byte for each coefficient. And we computed 452,000 out of the 453,060 rows of the Cauchy-Linguistic polynomials in 14 hours. And then the computer crashed, which was annoying. So the computer got rebooted on the 22nd, and we restarted it and ran the computation again with more threads this time, and it finished in let's see, elapsed time 40,229 seconds. That's 11 hours. Same number of polynomials as before. And so we needed to do these computations for 4 different moduli so that we could do a Chinese remainder theorem and get actual answers. So on December 23rd, we started a mod 255 computation, and the computer crashed. And it took them 3 days to reboot the damn computer. I don't know why, but anyway, on the 26th, the computer was rebooted. We wrote down the polynomials modulo 255, and we started computing mod 253, and halfway through the computation, the computer crashed. So this was a borrowed computer, which somebody else had bought with $100,000 of NSF grant, and we were getting slightly worried that we were doing something. So we asked experts whether we were causing this computer to crash. So we decided that we were not going to abuse the computer anymore for a year. So that was on December 27th. So on January 3rd, we were all a year older. There were 30 of us, so we were 30 years wiser. So it was safe to go back to work. So we did the mod 253 computation. And actually, we only needed 3 moduli, as it turned out. And so we had these answers in these 3 moduli, and so the Chinese remainder theorem says if you know something modulo 253, 255, and 256, you know it modulo the product of those 3 numbers, which is that. So that's a tiny little computation for each of the 13 billion coefficients that we had. So the mathematician programmer started his Chinese remainder theorem software, and we always wanted to see how these calculations were going. You don't want to start a 20-hour computation and just have a blank screen staring at you. So he put a little counter that displayed the number of the polynomial that we were computing. So the screen displayed 0, then 1, and so on up to 1 billion. It turns out that displaying a number to the screen takes a while. And so this was a bad idea. So we started over. This time the counter only flashed every 4,096 polynomials. And that was going fine. Except that Sage crashed in the middle. So the owner of Sage decided that the hard drive on Sage was sick, and he replaced it. And because he's our hero, he had backups of the files that we'd computed. And so on January 5th, we started this computation again, and the output file came out to be 7 gigs bigger than it was supposed to be. And that was because there was a bug in the output routine. Since there are 1 billion of these polynomials, somewhere the number of a polynomial had to get multiplied by 5. and the numbers were 4-byte integers. So if it got multiplied by 5, if it went above 4 bytes, there's a problem. And so that's why the bug only showed up at polynomial 858 million. But Mark found the bug, and on January 7th, started it again, and on January 8th, wrote down all of these polynomials. That's what was called the character table for this group. So, who cares? So, here's one kind of answer to who cares. So, 3 years before this, Foucault was at MIT. He was visiting there, sharing a room with another Atlas member, a young guy named Don Chubutaru. So he was halfway through writing the software, that point where you can't see either the end of the tunnel or the beginning anymore. And they were going home one day after a weekend of mathematics, and Don said, "Foucault, look at us. We're spending Sunday alone at work." And Foucault was startled by this remark, but he was never at a loss for words. He said, "I don't know about you, but I'm having the time of my life." So that was Foucault du Clou, and that was the point. And that's the end. Thank you. Everything was too simple for questions, probably.
Any questions from the audience?
A mundane question. I missed when you started the computer programming.
So Jeff Adams said we should have a computer program to do this stuff. He said it in 2002. And Foucault started writing code immediately, working out all the structure of these various groups. And, you know, the code could do more and more things as he went along. And finally, to get it to the point that he could compute these Kazan-Lustig polynomials, these character tables, that's he finished at the end of 2005. So sort of 3 years of work. And I mean, since then, there's a guy named Mark van Leuven who's continued to extend the software. There are always more questions to ask, more things you want to know.
And the computer you used was?
It was. I've never actually seen Sage. I mean, it's at the University of Washington. I mean, it's a Linux box. You know, it had, at the time, it had I think 64 gigs of RAM, and I don't remember 16 or 32 processors, some number. We did multi-thread some of the computation and speeded things up that way. Now, you know, I have fluid dynamics friends at MIT who have computers with 256 gigs of RAM and 128 processors or something. We can do all these things much faster.
So it has been converted, or has it been faster?
Oh yeah, I mean the code's written in C++, so it's that's one of these things that's brought along all the time in any new. Well, I say that with a wave of course, every time there's a new operating system, it doesn't work anymore. But these are small problems.
I guess I know at Harvard they're using video cards and so forth because they have so many parallel processors.
Yeah.
There you have it.
Yeah, that's so. We used something called. POSIX. There's some multi-threading language that's a typical Unix part of C++. I mean, it has to do with C, actually. And again, this is something which somebody else does the work of dealing with new computers.
So how many similar polynomials did we find that E8 contained?
How many, sorry?
Similar polynomial, the KL polynomial?
So there were a little more than 1 billion distinct polynomials.
And each
How many pairs turn out to be 1?
That's an interesting question. This I don't remember. I mean, my guess would be a majority, or half-ish. But I don't actually know that. There's a window here somewhere. It's a danger to show other people your computer, but this is some slightly different polynomials for a much smaller group, but let's see. Oops. Well, you can see there's a string of ones there. So maybe it was an exaggeration to say that most of them. It was probably an exaggeration to say that most of them were. Well, if we go further down, yeah, that's. But on the other hand, you also see it's really hard to get intuition about how complicated these things are, because they get more complicated as things get bigger, and it's really complicated to understand how much more complicated. So this E8 group is 248 dimensional, and to do this calculation we had to use all sorts of modular tricks, and it ended up using about 40 hours of CPU time and 60 gigs of RAM. There's an exceptional group called E7, which is 133 dimensional. It's half the dimension. The computation runs on my laptop in 5 minutes, something like that. I think that's right. It's things get worse. Yeah, yeah.
So since then, I know that we have algorithms to check for you.
Yeah. So the algorithm for unitarity exists. The mathematics is done. In order to, for many groups, the programming is done. If you want to deal with all groups, you need some generalization of the Kazhdan-Lusztig polynomial. That's actually what's listed here, something called twisted Kazhdan-Lusztig polynomials, because the original Kazhdan-Lusztig polynomials, the coefficients are all positive, non-negative integers, but here they aren't, though it's hard to see that. Did you see a minus sign? Okay, they're here somewhere. There, minus Q. There's a minus sign. So you need to teach this software to compute these twisted things, and we haven't done that yet. I mean, these answers are this is from code that Mark wrote yesterday, and it now does this example correctly. this is the SO55 example, but we haven't figured out how to fix it. It's, you know, the mathematics is done, but coding it is painful.
That's what you do for the C.
So that's right.
So is it right to think about the polynomials as representations of the 8?
They're information about representations. There are a whole lot of levels of encoding. So representations get coded by some functions called characters, and the characters are involve more or less trigonometric polynomials, and so there's various exponentials with integer coefficients. So the whole problem is to figure out what those integers are, and the values of these polynomials at 1 are the integers, and the Gaussian and Lustig, you know, people had been trying to compute these integers for decades and never getting anywhere. Gaussian and Lustig realized you can't compute them as integers. You can only compute these polynomials whose value at 1 is the integers. The algorithm for computing the polynomials doesn't just use their values at 1. You have to compute something more than you need in order to get something easy at the end.
So we started with the talk about linear algebra and how we go from permutation to different type of matrices in our church.
Mm-hmm.
What's the relationship between these and matrices?
So E8 is playing the role of invertible n by n matrices, and permutations, the permutation group is what's called the Weil group for n by n matrices. It's, if you want to specify the eigenvalues of an n by n matrix, you have to give n numbers up to permutation. And in E8, more or less, you have some Weil group which is telling you how to specify eigenvalues for elements of E8. That's the pretty crude. Sorry.
How many cores do you think you could, or how many CPUs do you think you could run on it before you lose the benefit?
It depends on exactly what the computation is. So all of the part that was multi-threaded was this business of, for every primitive pair, calculating some polynomial. And so you could have, you know, as they say, there were 6 billion primitive pairs here, and so you could have thousands of processors working at the same time. But, well, thousands. The difficulty is when one of these little computations finds a polynomial, you know, it computes a polynomial, it goes to look to see whether this is already a known polynomial, and if it's already known, then it just writes some number and everything's fine. But if it isn't already known, then it has to write this polynomial to the list of polynomials. And that's where the different threads can interfere with each other. And so in practice, we haven't used more than, I don't know, 30 or so threads, because otherwise they just end up spending all their time, I forget what the process is called, when, you know, one of the threads has to lock the store while it writes to it, and then the other threads sit there, you know, tapping their toes, waiting for something to happen. And so, but you know, that's kind of that's not an intrinsic mathematical problem. You know, if you broke the store into 10 pieces or something, you could presumably cut this problem down by a factor of 10. And I tried doing something like that, but I'm not a programmer and it failed. But, you know, there's a lot of room.
Is the software, is the source code available?
Yeah, so the my friend Jeff Adams has a web page. Oh, sorry. Of course, I'm not connected. So the software is called Atlas, and so if you can remember Atlas and atoms, you know, you'll find it.
Also, if you go on my webpage, you can find it.
Yeah, Alfred Noel wrote some pieces of this software too. There are lots of people involved.
Any more questions? Well, should we thank the speaker again?
Thank you very much.
Thank you.